Hello everyone, welcome to our discussion of section 6.3 where we will introduce partial fractions as one of the techniques for integration. So here the main idea is that sometimes we have fractions that are too complicated to integrate from the get-go. So we need to break these fractions up to smaller ones before integrating. So that's the main topic of this section. But before we can do that, before we can go over examples of that, we need to remember some of the skills we learned in previous math classes. Here's a short list of those. Long division, which we discussed in pre-calculus 1. Factoring polynomials, which we've been talking about since college algebra. Completing the square in a quadratic equation, multiplying both sides of an equation by the least common denominator in order to clear the fractions on both sides, and the discriminant. Remember, in our quadratic formula, a part of it is called the discriminant, and that's the part you see in red ink here, b squared minus 4ac, given that the quadratic equation is in this form. Then the discriminant piece is that. And if the discriminant is a negative number or less than 0, as shown here, then the quadratic function cannot be factored. So in cases like that, then we don't need to use the partial fraction for the denominator. We don't need, if this happens in the denominator, if we have a we call these prime quadratic equations when we cannot factor them, when the discriminant is a negative number, then we call those prime quadratic equations. And when this happens in the denominator of a fraction, then we don't need to use partial fractions. So we will use other techniques that I just mentioned, one of them being the completing the square. So we will probably use that rather than using partial fractions. And some of these things can be used in conjunction with partial fractions. Okay? But specifically, if the discriminant is negative, for a quadratic expression in the denominator of a fraction, then we don't need to use partial fraction. Okay? I will go over some, this is stuff you already know, or you've already seen in previous classes. I'll go over maybe long division and completing the square before tackling some of the problems for this section. So we'll do that. At least you'll have a brief refresher on that topic, which should be good. So as an example of how we did the long division, so suppose we have an example like this. If you already remember how this is done, please pause the video and obtain this, apply the long division and obtain the result, and then we'll compare solutions. And this goes for all the examples that are upcoming. Please pause the video before you see my solution, and then once you're done with your own solution, maybe don't take more than 20 minutes, 10 to 20 minutes, depending on the difficulty of the problem. But make sure you write down your own solution before you look at these solutions that you see in the video. Okay, so I'm assuming that you've done that, and now you're back. So here we set up this long division like that, and we have this polynomial divided by this. And so the first thing we do is we'll look at the first terms in the polynomial that we're dividing and in the divisor. And we ask, what term should we put up here such that if we multiply it by this first term, we will get exactly the first term in the polynomial we're dividing. So in this case, it's clear that that term is 2x squared, right? If we multiply that 2x squared by this first term, we will get that. Now that we figured that out, now we have to multiply this by all of the terms in the divisor and write the result underneath this polynomial. Okay, so let's do that. So we have 4x cubed as we expected. Then we have to distribute this to 1 as well. We get 2x squared. And we want to subtract this result from the expression above it. Right, so 4x cubed minus 4x cubed, we get 0. I'm not going to write it down. We don't have any x squared term in this polynomial, right? So all we have is this minus times that. So we write minus 2x squared. We don't have any x term in this expression. All we have is 7x up here. So 7x minus nothing, which means we got to write the 7x as is down here. And then also there is no constant value here, so we can subtract it from 7. So 7 minus nothing, we get 7 itself, right? Plus 7. Now we repeat what we just did for this polynomial. We look at this first terms, this one and that term, and we ask what term can we write up here so that if we multiply it by 2x, we get this first term, minus 2x squared. And clearly that is minus x, right? Minus x times 2x, we get minus 2x squared. Like that. And then we have to distribute this minus x into 1 as well. So let me do that. Minus x. As soon as we're done with distributing this into both all the terms inside the divisor, we subtract this whole expression from the expression above it. So a minus there. So we have 2x squared minus 2x squared minus 2x squared. These two cancel each other out, right? They add up to 0. And then for the x terms, we have 7x minus x. This minus will make this positive. We get 1 positive x here. 7x plus x is 8x. And then again, once again, there is no constant value here, so we can subtract it from 7. As a result, we'll just write down the 7 here as it was. Okay. So once again, we want to repeat what we did, and we compare these two first terms, 2x and 8x. What value or term we can put up here so that if we multiply it by 2x, we get 8x. And that's clearly positive 4, right? So once we know that term, we got to distribute it to all the terms in the divisor and list the result here. So we have 4 times 2x, 8x. 4 times plus 1, that's plus 4. We're done distributing, so we have to subtract this from that expression above it. And so 8x minus 8x, that's just 0. 7 minus 4, we end up with 3. Now, at this point, if you compare these, there's nothing we can put here and multiply it by this first term in the divisor and get some 3, right? So this is the point where we stop because this is our remainder. So this becomes our remainder. We cannot continue the long division beyond this point. So this is the remainder, and if we get a 0, then we have a perfect factor of that polynomial. If this was 0, then this times whatever these two would be complete factorization of that original polynomial. But because we have a remainder, this expression is not a complete factor of that. In any case, once we have a remainder, we can write the result as this. The original polynomial, we can rewrite the original polynomial as 4x cubed plus 7x plus 7 equals this divisor, 2x plus 1 times that, 2x squared minus x plus 4 plus the remainder that we have, that result. Okay, so this would be our the result of the long division. So this is just a quick refresher on the long division procedure. The other thing we should know is when we factored polynomial in pre-calculus, we talked about finding all possible rational zeros, right? Because a polynomial can have any kind of root. It can have complex roots, it can have irrational roots, it can have rational roots. But we talked about a technique for finding possible rational roots or rational zeros of a polynomial in pre-calculus 1. And that formula was, so first we identify the possible roots, and then we test them one by one in the polynomial, and then that will help us identify all the rational roots of a polynomial. But this is the formula to find the possible ones. So all the factors of the constant term in this example that I've shown here, that would be all the factors of the constant term -8 divided by factors of the leading coefficient. Leading coefficient, as you know, is the coefficient of the x term with the highest power, right, in the polynomial. So that's +1 here. And then that gives us all the possible rational zeros, and then we'll test them one by one, and if necessary, use the long division to figure out a factor of this polynomial. As you'll see, when we get to partial fractions, factoring a polynomial or factoring expressions is extremely useful and necessary for the procedure to work. Okay. All right, so once again, I hope you pause the video lesson and use a scratch paper to spend maybe 10 minutes or so on this, 10, 15 minutes. Maybe 20 minutes, but no more than that. And then whatever you end up with, you can compare with this solution. All right, so the constant term in this case is the -8. Let's find all the factors of it. So we have ±1, ±2, ±4, ±8. And then, of course, the leading coefficient is 1, so the factors of 1 are ±1. ±1. So -1 times -1 gives you +1. +1 times +1 gives you +1. Okay, that's the idea. All right, so now that we have that, if we go by this formula and divide all these numbers by ±1, what do we get? We get these back, right? Divide all of these with this, you get the same numbers back. Okay, so possible zeros are all of that. Like that. Okay. So now it's impossible for all of these to be the roots of the polynomial, right? I'm just reminding you what we talked about in pre-calculus 1, because the maximum number of any kind of root this polynomial can have is equal to the highest power of the x, or the independent variable in the polynomial, so 3. So for sure, we can't have 8 roots. Only 3 of these will be valid. So we can start by testing one of these, say the first one, the +1, right? Let's put +1. Let's test +1 in this expression and see if we get a 0. If we do, then x minus 1 is a factor of that polynomial. We already know that. And that's the format for the fact. If any of these numbers leads to a 0 in this polynomial, x minus that value would be the factor of that polynomial. Which means if we have a factor, we can use the long division easily to find the other factors of the or at least some or most of the other factors. So I'm going to test positive 1, just as the first number to test. Okay, so testing x equals 1 in this polynomial, we will get so we get 1 cubed minus 7 times 1 squared plus 14 times 1 minus 8. Okay, so then we have, so that's 1, that's minus 7, so we get minus 6 here, minus 6 and minus 8, that's minus 14, plus positive 14, we get 0, right? So this leads to 0. So we did find, just by testing the first digit, a complete factor, a factor of this polynomial. So x minus 1 is a factor of that polynomial. So let me write that down. Again, all of this material, this stuff is review. You've seen this before in pre-calculus 1. Is a factor of the polynomial. So because of this, then this is fortunate. So we can take this polynomial and divide it by x minus 1 to obtain another factor for that polynomial using long division, of course. So let's do that. So we have, what do we have? We have x cubed. I'm just going to rewrite it here. X cubed minus 7x squared plus 14x minus 8 divided by x minus 1. That, right? So just like what we did in the previous example, we're looking for anything we can multiply by x and get x cubed, the first terms, right? So of course that's x squared. X squared times x, we get x cubed. X squared times minus 1, we get minus x squared. And then of course then we will subtract this from the expression above it. X cubed minus x cubed, that's 0. Minus 7x squared minus x squared. So this will make this positive. So this will be minus 6x squared plus 14x minus 8. Okay, we repeat the process. So what term can we place up here so that if we multiply it by x, we get minus 6x squared. That's, of course, minus 6x. Minus 6x times minus 1, we get plus 6x. And once again, this minus that, we get 0. And then 14x minus 6x, that's 8x. And minus 8 minus nothing, right? Because there's no constant in this expression. So we'll just bring down minus 8 as it was, like that. Once again, we ask, okay, we already know we should get 0 at the end, in this case, right? Because we found that x minus 1 to be a factor of the original polynomial. So we know we're going to get a 0 remainder. And if we don't, that means we did something not correct in the middle of our calculation. But we expect to get 0. So if I put 8 up here, multiply it by x, I get positive 8x, which is what I want, right? So plus 8x minus 8. X minus 8x, that's 0, minus 8 minus minus, that's again adds up to 0, which we expected, right? So then the complete factorization of this polynomial is this x minus 1 times that. Let's write that down. I'll try to fit it here. So we started with x cubed minus 7x squared plus 14x minus 8. So we just found the factorization of that, x minus 1 times all of that, right? So times x squared minus 6x plus 8. Now, if this cannot be factored, we're fine. We'll just end here. But can this be factored? This is just a easy quadratic equation, right? So what two numbers multiply to positive 8 and add up to minus 6? So that's plus or minus 4 and minus 2, right? So minus 4 and minus 2 multiply to positive 8 and add up to minus 6. So we can write a quick factorization of that as well. Breaking this up into factors, we get x minus 4 times x minus 2, like that. So this is the complete factorization of the original polynomial we had. Notice how we started. We started by finding the possible zeros using this formula, right? Using this formula, we found the possible zeros. We tested one, and it turned out to be, fortunately, a zero of this, or a root of this polynomial, that polynomial. And so we use that in our long division to obtain the other factors. Okay, once you know how this is done, all the other ones are exactly the same way. The procedure works the same way if the factoring or finding the possible rational zeros is a technique we can use. They're all the same. Okay. The other technique that we should remember in this section, and in calculus in general, is completing the square. So completing the square we talked about in pre-calculus 1 as well. So let's use this as an example to refresh our memory about this. And please pause the video, try this on your own, and then come back to the video after you're done. Okay, so I'm assuming you've done that. Now recall that completing the square can be used if the coefficient of the quadratic term is positive 1. Is that the case in here? No. So we need to factor this expression in order to make sure that this coefficient is positive 1. But before that, let me just write a note on that. Note must be positive 1. Okay, so let us factor this. Move this up a little bit. Factoring, we have 3 times x squared plus 3x plus 5 over 3, right? So now the coefficient of this quadratic expression is positive 1, and we can apply this completing the square technique to this. Okay, and the way that technique works is first we take the b term, right? B is the coefficient of the x term, right? We take that, and whatever that value, we divide it by 2, always divided by 2. So 3 divided by 2. So divide b by 2. And by saying b by 2, I'm referring to the familiar form of a quadratic equation, right? Let me write it here. ax squared plus bx plus c, right? Remember that? So the coefficient of the quadratic term is a, coefficient of the x term is b, and the constant term is c. So b, once we have the coefficient of the quadratic term as positive 1, whatever b is, we divide it by 2. In this case, we end up with 3/2. Okay. Then, this is positive 3/2, so x plus positive 3/2 squared, right? As soon as I do this, I have solved one problem and I have created another problem. Because if you disregard this 5/3 for a second, well, I mean, by disregard, I mean, let me write it here. Right, let me write it here. Now, once I wrote this expression, now I have a perfect square. Now I've completed the square, right? So I solved one problem, but I created another one. And the problem I created is that I created an additional value that wasn't there before. So x squared is x squared. 2 times x times 3/2. That's just going to give us 3x, right? So far, so good. We get what we had. But then plus 3/2 squared, I get positive 9/4. I get a positive 9/4, which wasn't here before, right? So how do I deal with this problem? With this problem of having an additional 9/4 value? Well, we simply subtract it. Subtract 9/4. Now, if you expand this, x plus 3/2 squared, and then subtract minus 9/4 from it, you end up with exactly x squared plus 3x. Okay, and of course 5/3 is out here. Okay, so let's just combine these two constants and write the final result here. We have equals 3 times x plus 3/2 squared. So common denominator is 12. 12 minus 27 and plus 20. So that will give us minus 7/12. Okay, and let's not forget this 3 out here, which is distributing itself to all of that. So that's after we completed this square for that expression. So this is that technique. Just remember, before you apply this technique, the coefficient of the x squared term has to be positive 1. So in this case, it wasn't, and we had to factor the 3 out, so we could get that in there. Okay. All right. So next, I think that's a good refresher on some of the techniques we use for obtaining partial fractions. Now, there are several cases for obtaining partial fractions. Case one is that if we have a rational expression, and remember, partial fractions, we're using them because we want to break up more complex fractions into easier ones, smaller fractions, right? So if we have a rational expression like that, such that the degree of the numerator, that is px, is less than the degree of the denominator, qx, and such that the denominator qx is a product of distinct linear factors, none of which is repeated. So these are distinct linear factors. In such cases, there's no need to apply long division, mainly because the degree of the numerator is less than the degree of the denominator. Okay, so it's not applicable, and so there's no need for that. So we can simply write our partial fractions without doing any of those techniques. We can go directly from this form to partial fraction form. So let's see an example of this type. So here's 1. If you already have some familiarity with partial fractions, go ahead, pause the video. Or if you've read the book already, go ahead, pause the video and carry this out all the way to the end and integrate it, basically. Convert this to a partial fraction and then integrate the result. And hopefully our answers match. But if not, then you can either read the book first and then come to this example. What I'm trying to do is encourage you to write down your own solution before you see my solution. That's the idea. So either read the book or from memory solve this and see how far you get before you watch this solution. All right, so I'm assuming you've done that. Now, before we apply the integration, we need to break this up, right? So x minus 4 divided by x squared minus 5x plus 6. This is a simple quadratic equation. We can factor this, right? So we can write x minus 4 divided by, we're looking for two numbers that would multiply to positive 6 and add up to minus 5x. So x minus 3 times x minus 2. Okay, so that's a factorization of that. Now that we have that, so let me add a note here. So because the denominator, as case 1 said, has two linear factors, we say linear factors because the variable x has power 1. So i.e. variable x has power equal to 1. That's a linear factor, right? Then, and notice none of these are repeated, right? Like what this is saying, it's a linear factors, none of which is repeated. So none of these are repeated. What would it look like if they were repeated? So we would have x minus 2 squared or cubed. So then we have a repetition, right? Because it's x minus 2 times x minus 2 times x minus 2 if it's x minus 2 cubed. Or if this was x minus 3 squared, we would have a repetition because that would indicate x minus 3 times x minus 3. But in this case, they're not repeated. The powers are 1. So we need here we need to use two partial fractions. Okay. And let us do that here. We have x minus 4 over all of that. Over x minus 2. You notice what happened? So a and b are to be determined. Each linear factor, each non-repeating linear factor is the denominator of each fraction here, and we need to determine a and b in order to break this bigger fraction into smaller ones. Okay, so to remove fractions then, we have to multiply both sides of this equation by that factor, x minus 3 times x minus 2. So let me write that. So to remove fractions, multiply both sides x minus 2, like that. Okay, so if you do that, you know that is a factorization of this denominator, and if you multiply this fraction by that, that will cancel with these, so you end up with just x minus 4 on the left side, right? So let's write that down here, x minus 4. On the right, if you multiply this fraction by that, x minus 3's cancel out. We end up with a times x minus 2, and then plus b times x minus 2 will cancel out. We end up with b times x minus 3. Like that. Okay. Now we, on the right side, let's distribute and simplify a little bit. So we have ax minus 2a plus bx minus 3b. Okay. Now compare this. Well, let's combine all the x terms on the right. So we have x minus 4 equals a plus b times x, right? I'm just combining these two and factoring x out. A plus b times x plus minus 2a minus 3b. Those are constants, right? And a and b are, we're trying to figure those out. So if you compare the right side with the left, a plus b should be equal to 1, right? Because if the left side is to be equal to the right side, the only way that could happen is if a plus b equals 1, and minus 2a minus 3b is equal to minus 4. So let's set up a system. So a plus b has to be equal to 1, minus 2a minus 3b should be equal to minus 4. So I'm not going to go through the solving this. This is a pretty easy, simple system to solve. So I'm just going to put down the result. So after you solve this system, we should agree that a would be equal to minus 1 and b would be equal to or is equal to 2. So now we replace a and b with this result. Okay, let's do that. So thus we have on the left x minus 4 over that factorization we had. And x minus 2 is equal to, instead of a, we have minus 1. So minus 1 divided by x minus 3 plus 2 over x minus 2, right? Like that. All right, so the original integral, that one, we can write in terms of integral of these two terms. So let's do that. So therefore, we have the original for integral from 0 to 1 x minus 4 over x squared minus 5x plus 6 dx is now equal to integral from 0 to 1 of all of that, of these two. So we have 2 over, I'm just going to put this minus 1 in the middle, so 2 over x minus 2, right, minus 1 over x minus 3 dx. This is, so that minus 1 is now in here. Okay, so then this is an easy integral. So we can write 2 times natural log of x minus 2. So let me write that down here. 2 times natural log of x minus 2, right? And if you take the derivative of this, you get 1 over x minus 2 times derivative of x, which is 1. So it would be neutral. and then times 2, it will give you 2 over x minus 2. And then for this one, we'd have minus natural log of absolute value of x minus 3. Like that. And then, of course, this is evaluated from 0 to 1. Okay. So then we take this one step further, just replacing for x with 1 and then 0. We have, okay, so we have 2 times natural log of 1 minus 2 minus natural log of 1 minus 3 minus and 2 natural log of 0 minus 2 minus natural log of 0 minus 3. And the absolute values will make these positive, right? So that's that. And then we have, so this is natural log of positive 1. It's 0 times 2. Well, let me write it here first. Natural log of 1 minus natural log of 2, right? I'm writing after we apply the absolute values. And then minus 2 natural log of 2. Minus times minus is positive natural log of 3. Positive 3. Okay, so this is 0. We know that this is 0. And the rest we can write as it is. So we have minus natural log of 2 and minus 2 natural. So that would give us minus 3 natural log of 2, right? Minus 3 natural log of 2 plus natural log of 3. Like that. Okay? Like that. All right, so I hope that agrees with what you had on your own, in your own solution there. So that was case 1, where we have non-repeating linear factors in the denominator. All right, let me bring it back. That's case 1. Non-repeating linear factors in the denominator, right? So case 2, if we have a rational expression where qx, or the denominator, is the product of linear factors, some of which are repeated, right? So some of them have a power higher than 1. If that's the case, then we must factor the denominator as far as possible. And step 2, only if the degree of the numerator is larger than the degree of the denominator, use the long division to obtain that. And then we can then break up this piece. This one we can easily integrate, but this still being in a fraction form, we should then break up either this or that piece into a sum of partial fractions of this form. Okay? So 2 and 3 are very closely related, as is step 1. Okay, so that's the procedure, but most importantly, we should do this when we have product of, in the denominator, we have product of linear factors, some of which are repeated. Okay, that's the case where we can apply this technique. All right, so having seen this previous example, hopefully that will give you some clue for this one. I want to encourage you to write down your solution before you compare it with this. But beforehand, note, a note for this problem is that because the degree of the numerator is smaller than the degree of the denominator, right? Here we have x squared, and then in x we have x cubed if you multiply them. Here we have x squared. So x squared is smaller than x cubed. And because of that, there is no need to apply long division here. Okay? And we wouldn't be able to apply it anyway, but so that technique is right away out of the question. Okay, so let us then break this up in partial fractions. So we have x squared minus 5x plus 16 divided by that. So 2x plus 1, x minus 2 squared. So then we have, this is a linear factor, right? So we can write equals a over 2x plus 1 plus b over, we have a repeated factor here, so we list that one time as b over x minus 2 with power 1, and then the third fraction, c over x minus 2 squared. So if this was cubed, we'd have to have d over x minus 2 cubed. So we have to write one fraction for each power, increasing the power all the way to the highest power. If you had x minus 2 to the fourth power, we would have to have e plus d plus e over x minus 2 to fourth power, all the way from a, b, c, d, and e. Okay, all right, so we do exactly what we did before. The common denominator here, or the denominator of this side is x minus 2 squared times 2x plus 1. So we multiply both sides of this equation by this denominator. Of course, on the left, they cancel out. We end up with just that, right? So I'm going to write down x squared minus 5x plus 16 equals. Now, if you multiply this by this fraction, 2x plus 1 and 2x plus 1 cancel out. We end up with a times x minus 2 squared. If we multiply this whole denominator by this fraction, x minus 2, one of the x minus 2's will cancel out with this. We end up with 2x plus 1 times x minus 2, so plus b times 2x plus 1 times x minus 2, plus, if we multiply all of this by this fraction, x minus 2 squared and x minus 2 squared cancel out. We end up with plus c times 2x plus 1. Okay? So now, again, we have to simplify this and figure out what a, b, and c are. So let's take steps in doing that. That's that. And then, so just double checking this, and then 2x squared minus 4x and plus x, that will give us minus 3x minus 2 plus 2cx plus c. Okay. Then let's see. So we have to distribute these. Minus 4ax and plus 4a plus 2bx squared minus 3bx minus 2b plus 2cx plus c. So once again, we have to combine all the x squared terms. That would be a plus 2b and x squared factored out from these two terms, right? We get that. Then the x terms are this one, and that one, right? So we have plus minus 4a minus 3b plus 2c. Factored out, x has been factored out of these three terms, this one, and that. This, that. And then the constant terms are, these are the terms that are not associated with x in any way. So we have 4a here. What else do we have? We have minus 2b here. And then we have a c here. Right? Like that. Okay, so we can now write our system. If these two sides, this side and this side, are to be equal to each other, then a plus 2b should equal to 1. All of this, the factors of x, should add up to minus 5. And these constants, all of them, should add up to positive 16. So let's write the system down. So from this side and from that side, we can write our system. We have a plus 2b should be equal to 1. All of that should be equal to minus 5. Right? I'm just double checking now. Okay. And all of this should be equal to 16. Like that. Okay. So I'm just going to do this very quickly here so we don't take so much space, because this, again, is a topic. Solving these systems using the elimination method is something we've covered in previous classes. So I'm just going to briefly mention it here. I'm just going to recap what we do. So eliminating the c terms in the last two equations. And I trust that if you have any questions about this that we've looked at in the previous semesters, then please stop by the office and ask me about it. So eliminating the c terms in the last two equations, we have, and we end up with this. So this is basically what we're doing. We're eliminating the c term. So minus 4a minus 3b plus 2c equals minus 5. And this is, I'm multiplying the bottom equation by minus 2. And this is what I get, minus 8a plus 4b minus 2c equals minus 32 on the other side. Okay, and then adding these two equations, we have minus 12a and then plus b, and then the c terms drop out as we planned. And this is minus 37 on the right side. So we have this reduced equation here, and then we set this up in the same system with this one, which had a and b in it. And so we have, let me move this up a little bit. So we have a plus 2b equals 1. And this one, minus 12a plus b equals minus 37. Then if we solve this together with the original system, and this is the part I'm going to skip and I'm going to let you verify this, a should be equal to 3, b should be equal to minus 1, and c should be equal to 2. Okay? Now, with a, b, c determined as such, we can convert this integral to the integral of these three smaller fractions. Okay, so let's do that. So we have the original integral. I'm just going to rewrite it in this corner as x squared minus 5x plus 16. dx is equal to, then we have, so a was 3, so 3 divided by 2x plus 1. b is this parenthesis was not required, so I'm just going to erase this later. Or well, let me put a bracket here. But this was not necessary anyway. So minus that 1 over x minus 2. Okay, and then plus, I'm just filling in for these fractions. A being 3, b being minus 1, and c being 2. Okay, that's all I'm doing down here. Minus 1, and this parenthesis was not necessary. And then plus 2 divided by x minus 2 squared. And then we can close the bracket here, dx. Okay, so please disregard this parenthesis. Just the bracket would be fine. Okay, so all of these are pretty easy integrals, right? So we have, this is just 3 times, let me use a scratch paper here, because I don't have much space here, so let me just show that here. So this first term really is 3 times integral of 1 over 2x plus 1 dx, right? So this is, if we integrate this, we will get natural log of 2x, absolute value of 2x plus 1, but we gotta be careful, because when you take the derivative of this, it'll be 1 over 2x plus 1 times 2 by the chain rule. So in order to get rid of this 2, we need to multiply this integral by 1/2, which means it'll multiply it by this 3, and we get 3/2 times natural log of 2x plus 1. Okay, so we have 3/2 natural log of absolute value of 2x plus 1. That's the integral of the first one. Then minus natural log of x minus 2, or absolute value of x minus 2, plus, this is just because of this power. So we have, let me also do this on a piece of scratch paper. So that one, that last term, is simply 2 times integral of 1 over x minus 2 squared dx, right? And this we can write as 2 times integral of x minus 2 power dx, right? and then we can take the integral of this or integrate this by add a plus 1 to that power. We get minus 1, and then divide by the minus 1 power, so we get x minus 2 to minus 1 power divided by the new power minus 1. And of course, there's a 2 in front here, right? So what do we end up with? It's just minus 2 times x minus 2 to minus 1 power, or minus 2 divided by, put this in the denominator with a positive power, x minus 2. So that would be the result. Okay, so we have, so this should be minus, let me put a minus there, minus 2 over x minus 2. So that was not a plus, it was a minus. Okay, and of course, because this is an indefinite integral, we should have a plus c at the end for the constant, right? So I'll try to fix that. It should be just a minus. Okay, like that. All right, so next we have case 3. Here, case 3 is such that if we have a rational expression such that the qx, or the denominator, contains irreducible or non-factorable quadratic factors, if that occurs when the discriminant is less than 0, none of which is repeated. So that's all of this defines case 3. All of this conditions defines case 3. If the denominator is non-factorable and quadratic in form, and none of the factors are repeated, so they don't have a power 2, power 3, and so on. And of course, if the degree of the numerator, px, or the numerator is larger than the degree of the denominator, qx, we must use long division. Okay, and the partial fractions that we will investigate, and I intentionally put this in red out here, I wanted it to stand out. So the partial fractions that we will investigate, these are the partial fractions that we investigate, will be of this form. It will be of this form, but we may not end up with the same form, because let's say if b turns out to be 0, then we end up with a constant value over x squared plus 1. Or if d turns out to be 0, we end up with just a constant over that. So initially, when we set up our partial fractions for this case 3, they're going to be of this form. But sometimes b or d, or both b and d, turn out to be 0. So we don't end up with an x in the numerator. Just be aware of that. Okay. And here's one of the integration formulas that I thought would be useful to put on this sheet, because it'll come up in the upcoming examples. So if necessary, integrating a partial fraction such as this form can also be achieved using the following formula. So if you have that integration, then you can write 1 over b inverse tangent of x over b plus c. And b can be anything that you can, any value that you can write in a perfect square. So can you write 2 or 3 as a perfect square? Yes, you can. You can write, for 3, you can write square root of 3 squared, right? For 5, you can write square root of 5 squared is 5. So that's what we're talking about, all right? All right, so let's look at an example of this case, case 3. So you might want to go ahead and just pause the video, spend about 20 minutes on this, see how far you get. Hopefully you can finish it, and then come back to the video and we'll compare these. Okay, I'm assuming you've done that and now you're back. So first thing is, when we look at the denominator, we want to factor this. That's the first thing we've done so far, right? So let's do that again. And this is an easy expression to factor. So x cubed minus 2x squared plus x plus 1 divided by that, x to the 4 plus 5x squared plus 4 can be written as this, right? So x squared plus 1 times x squared plus 4 will give us that. Okay, so just a reminder, since this is one of the conditions of this case 3, I'm just going to make a note for it here, that note that we have non-factorable or irreducible quadratic factors in the denominator. Okay, so that's one of the conditions for having this case 3. So then we're going to set up for each of these quadratic. Notice if I bring this example back, the only fraction that had an a or a single constant divided by that was the one that had a factor in the denominator that was a linear factor, right? So the linear factor ends up a constant in the numerator. But the other ones are quadratic in nature, so the numerator ends up with bx plus c and then dx plus e. You can't have a constant like a b up here. It has to be bx plus c because you have a non-reducible or non-factorable quadratic denominator here. Okay, that's why we have bx plus c, dx plus c, because look at the denominators. They're non-reducible or non-factorable quadratic expression. But this one, where we just have a single constant in the numerator, has a denominator which is a linear factor. Okay? All right. So here, notice that both are non-factorable quadratic expressions, so we can't have a divided by this. It has to be ax plus b and then cx plus d divided by that. So let me write that down. Ax plus b divided by x squared plus 1 plus cx plus d divided by x squared plus 4. Once again, we multiply both sides by this denominator. What do we get on the left side? They cancel each other out. We get just that. On the right, if you multiply this denominator by that, x squared plus 1 and x squared plus 1 cancel out. We get ax plus b times x squared plus 4 plus cx plus d times x squared plus 1. Okay, so just like before, we have to distribute these things. plus d, and then combining these expressions. So do we have x cubed terms? We have two of them, right? This one and that one. So we factor x cubed, we end up with a plus c times x cubed. Do we have x squared? Yes, we do. We have this term and that term, so b plus d x 4ax and then cx, right? 4a plus c with x factored out. And then, of course, the constants are 4b and d. Like that. Okay? All right, so then comparing the right side with the left, a plus c should be equal to 1. b plus d should be equal to minus 2. 4a plus c should be equal to 1. 4b plus d should be equal to 1. Let's write all of this. So we have a plus c equals 1. b plus d equals minus 2. 4a plus c should be equal to 1. And finally, 4b plus d should be equal to 1. Like that. Okay. So then, comparing these, then we end up with, if you solve all of these, say, these two, the b plus d equals minus 2 and 4b plus d equal 1. If you solve those two together, or set those up, well, let me just do it this way. Let's pair up the equations that have similar or identical variables in a single system. So if a plus c equals 1 and 4a plus c equals 1, and then the other one is the pair where we have b and d. So we have b plus d equals minus 2, and then 4b plus d equals 1. So if you solve each pair, we have a equals 0 and c equals 1 from this system, and we have we should have b equal 1 and d equals minus 3 from this system. Okay, so now going back to this, we can replace for a, b, c, and d and integrate after that. So let's do that. Here's our original expression. I'm going to write it down again here, where we had integral of x cubed minus 2x squared plus x plus 1 divided by x to the 4th plus 5x squared plus 4 dx equals, and then notice that a turns out to be 0, right? So up here, 0 times x, that term drops out. We end up with just b, which is 1, over x squared plus 1. Okay? And then so hopefully maybe I can keep everything on the screen. Yeah, barely, like that. So now you can see how these replace a, b, c, d, right? So we have integral of 1 over x squared plus 1 dx, and then plus integral of substitute for c with 1, that will give us x plus d, which is minus 3. So x minus 3 divided by x squared plus 4 dx. Okay. In the next step, we can break this up even further, right? We can break up this as x over x squared plus 4 minus 3 over x squared plus 4, right? That's an easy transition. So let's do that. So we have integral of 1 over x squared plus 1 dx plus integral of x over x squared plus 4 dx minus 3 times 1, right? 1, just put the minus 3 in front like that, and then 1 over x squared plus 4 dx. Okay, like that. So just a reminder that for these two guys, this one and that one, and we can not this one, because this one has an x in the numerator, but when you have a constant divided by a quadratic term like this, and I want to remind you about this on the previous page, right? When we have 1 divided by a quadratic expression like that, then the integral of that is 1 over b times inverse tangent of x over b plus c. Just remember this formula, because now we're going to apply it. And that's when we have a 1 divided by a quadratic expression like that. We can't apply it to the middle term because that's an x divided by that, right? But we can apply it to this one and that one. So just in case, I'm going to put a reminder here, that one, and also that one. So we're going to, so using the formula, this one, integral of 1 over x squared plus a squared. Did I use a? Well, I used b squared. So b squared dx plus or equals, it's just on the previous page. So 1 over b times inverse tangent of x over b plus c for those two. Just for those two. Maybe I should highlight this as well. So just for that one and for that one. And that's that. Then we're going to have we're going to have an integral as follows. We will get inverse tangent. So this one, this is x squared plus 1 squared, right? So 1 over 1 is just 1. I'm not going to write it. So it's just going to be inverse tangent of x over 1 is just x, and then plus the middle one, that so that, notice that the numerator, if you take the derivative of x squared, you get 2x, right? So so this is natural log of x squared plus 4 divided by 2. Well, here's what I mean. Let me bring this scratch paper back. Right, this one. So for this middle term, the integral would be natural log of absolute value of x squared plus 4, right? But we can't leave it like this, because if we take the derivative of this, what are we going to end up with? We're going to end up with 1 over x squared plus 4. Then by the chain rule, we got to take the derivative of this and say 2x, right? So here we have just x, not 2x. So how do we get rid of this 2? Well, we multiply all of this by 1/2, right? So which means we multiply all of this by 1/2. So the integral of that would be 1/2 times natural log of x squared plus 4. Okay, because I don't have much room left here, I just wanted to show you that on a piece of scratch paper. But that'll be 1/2 natural log of absolute value of x squared plus 4, like that. Okay. Then the last one, of course, is that minus 3. Then this is x squared plus 2. 4 can be written as 2 squared, right? So in this formula, b would be 2. So minus 3 times 1 over 2 times inverse tangent of x over 2. And all of that, of course, plus c. I hope when I scan and copy scan this and post it on Web Campus, that c copies too, because sometimes when I scan it, they get cut off. Let me write it a little bit further to the left here. Hopefully that will show up on the scanned PDF version of this. So we have inverse tangent of x plus 1/2. Mostly I'm going to clean this up. These two are in good shape. 1/2 natural log of x squared plus 4. Now minus 3/2, and minus 3/2 times inverse tangent of x over 2 plus c. Okay, so this would be the final result. Like that. All right, I hope this was useful. Now let's look at another example. So here we want to evaluate this integral. And before that, here's a hint for you before you pause and solve this on your own. It says, note that the denominator cannot be factored. So this is a prime quadratic equation, which means it cannot be factored because the discriminant of this, or b squared minus 4ac, is negative. It's less than 0. This means at some point, completing the square should be used. So because we can't factor this, right? Because it's prime. So we need to have another technique to help us somehow break this up into better components than these. And completing the square is the technique to use when you get to that point. Okay? All right, that's just a hint. I hope you would go ahead and pause and carry out this solution. Okay, I'm hoping that you're done that, and now you're back. So I'm going to start by bringing to your attention that, notice that the degree of the polynomial in the numerator and the denominator are equal, right? 2 and 2. Because they're equal, we should carry out a quick or a small long division. But we should carry that out. So let me write this down. So we will use long division either if the degrees are equal or the degree of the numerator is larger than the degree of the denominator. Then we'll do that. But if this degree is smaller than this, no, we won't use long division. So quickly doing that, and I'll try to keep that on this screen. So we have 4x squared minus 3x plus 2 divided by that, 4x squared minus 4x plus 3. Just like before, we ask what term can we put up here to multiply it by this first term and get this first term. It's just 1, right? Put a 1 here. And now multiplying, we have 4x squared minus 4x plus 3. And then, of course, subtract all of this from the expression above it. So we end up with 4x squared minus this. We end up with 0. Minus 3x minus 4x, that's just a positive x. 2 minus 3, that's minus 1, right? So this is our remainder. Because whatever you put here, multiplied by 4x squared, you're going to get a higher x term than this. So this is where we have to stop, and this is what our remainder is. Remainder. And then so the original expression, which you can see at the top, can be written in this form. And I have to move this up. It can be written as so this is what we had. We take this 1 plus the remainder, x minus 1 divided by the divisor, like that. Okay. All right. So now, so this is irreducible, right? So now, after we did the long division, we still have a fraction with an irreducible or non-factorable denominator. This is where we still have to use another technique to break this up a little bit. We can't leave it like that. Okay? So to do that, we will use the completing the square. And I will make a note here just so that you have it in the notes. So 4x squared minus 4x. Remember, we did the long division because the degrees of the numerator and denominator were equal, right? So we did that. We always have to do that if that happens to be the case, or the degree of the numerator is larger than the degree of the denominator. And now, after that, we still have to apply the completing the square method to this, to the denominator here. Plus 3. Or non-factorable. So because the discriminant is negative or less than 0. So instead, let us complete this square in the denominator. So you can see in calculus, we use a variety of techniques we learned in the past. Okay? All right, so we start with that. Let me move this up a little bit. So we have 4x squared minus 4x plus 3 equals, remember this quadratic term should have the coefficient equal to positive 1 before we can complete this square, right? So let's factor out 4. From that expression, this is where we end up. The b term or the x term has coefficient minus 1. Earlier, when I gave you that short example or refresher on this, whatever you end up with, after you factor, whatever you end up with for b, you divide it by 2. So this, b should be divided by 2 always, so we end up with minus 1/2, and as soon as you have that value, you can write 4 times x minus 1/2 squared plus 3/4, right? So what happened here, if you expand this perfect square, what we created as a perfect square, if you expand it, you're going to get x squared minus x for sure, but you're also going to get plus or positive 1 over 4, right? Do we have a positive 1 over 4? No. We have a 3/4 here and a 3/4 here. So the positive 1 over 4 is an extra that we need to get rid of. The way we get rid of that is we simply say minus 1 over 4. And that will, now if you expand this, subtract minus 1/4 from it, you end up with exactly that term. For all of this, you get that. But the difference here, of course, is that we have a term that has been written in complete square form, okay, which is what we wanted. Okay, so now if I can fit it here, let me try starting everything from here. So we have, if we add minus 1/4 and 3/4, we get positive 1/2. So let me clean that up a little bit. 4 times x minus 1/2 squared plus 1/2, right? Like that. And then, so if we distribute this, what are we going to get? We're going to get 4 times that, and that will get 2. 4 times 1/2, we get 2 here. So after distributing, so let me do that. So we will get, let me put that here, 4 times x minus, or x squared. I'm just going to expand this. X squared minus x plus 1/4 plus 2, right? I just distributed I expanded this. 4 is multiplying itself by this and also by 1/2. This 2 is from multiplying 4 times 1/2, we get 2. Now, if you distribute this and combine this, I'm running out of room here, so I'm just going to put this ultimately simplified version here. Equals 2x minus 1 squared plus 2. So we did all of this to end up with a simplified version of that. So this is a simplified version of this, such that one of the terms is in perfect squared form. Okay? So now we're not done with this. So let me bring another paper here. Like that. Okay, so our original integral, so we can say thus, we started with this form, 4x squared minus 3x plus 2 divided by 3 dx equals, we ended up with this, right? So, but let me remind you, we had a 1 before that. Before this, it's on on the previous page. That we gave us, after the long division, we ended up with 1 plus that. Then we reduced this denominator to this. So replacing for all of that, let me write that here. Integral of 1 plus, that's that one that I just showed you, and then x minus 1, that 1 plus x minus 1 over what we just got, divided by that. So x minus 1 divided by 2x minus 1 squared plus 2. Close parentheses, dx. Okay, so now if we break up this in an integral, what do we get? We get integral of 1 dx, right? That's just x. If you integrate it, you get x, plus integral of x minus 1 divided by all of that, 2x minus 1 squared plus 2 dx. Okay, let me integrate this because it's just easy to do that right away and be done with it. So this gives us x plus the rest of that. Dx. Okay. All right. So now, looking at what we have in the numerator and the denominator, we have to use a way of integrating this, and it seems that substitution would help us do that, right? So if we take the letter u as substitution for 2x minus 1, then we will get 2 du would be equal to 2 dx. And then, so let's do that here. Let's see. So if we have, I'm trying to think if that will work, and then x would be 1/2. Yeah, that would work actually. Okay, so let's set, I've tested it before, so it should work. So set u equals 2x minus 1. So this, and then so we're using substitution, which we learned a little bit earlier. So this will give us, if we take the derivative of both sides, we get du equals 2 dx, which means then dx would be equal to 1/2 du, right? So dx equals 1/2 du. And then at the same time, from here, we can get a replacement for x. If we solve for x here, we get x equals 1/2 u plus 1. 1/2 u plus 1. Just solve for x using this equation, and we'll get that. So now for x, we have that expression to substitute. For this 2x minus 1 squared, we have u to substitute for. Let's do that. So we end up with x, which is that. Which is that, x here, x plus integral of, instead of x, I need to replace x with all of this. So we have 1/2 times u plus 1 minus 1 divided by u squared, right? U squared plus 2. And then, of course, times, instead of dx, what do we have? Instead of dx, we have 1/2 du. right? Like that. Okay. So now we have, all right, so we have, so we need to simplify this. 1/2 u plus 1/2 minus 1, that's minus 1/2. U over 2, so let me write it here. So x plus this 1/2, I'm going to put that in front. So 1/2 integral of, distribute this, we get 1/2 u, and distribute and subtract from 1, we get minus 1/2 divided by u squared plus 2 du, because this 1/2 is now in front. Move this up a little bit. And then, so here, now let's factor out 1/2 from the numerator here, right? It's now a complex fraction. When we factor that out, it's going to look a lot better. So x plus 1/4 of integral times integral u minus 1 divided by u squared plus 2 du. Now we can break this up, right? So let's do that. We have x plus 1/4 times u over u squared plus 2 du minus 1/4 again, because that belongs to the entire integral, minus 1/4 times 1 over u squared plus 2 du. Okay? All right, so now integrating that, this is, let me bring a scratch paper here because I'm running out of room again. So integrating that, you have u squared in the denominator and u, so that'll be natural log of u squared plus 2. Integrating that, if you write it like that and leave it like this, then it won't be correct, because if you take the derivative of this, you end up with 1 over u squared plus 2 times 2u by the chain rule, right? So in order to get rid of that, and we want the u but not the 2. The u is there. We don't want the 2. So we have to multiply this by 1/2. Okay? And then, of course, times 1 over 4. So 1 over 4 times 1/2 times natural log of u squared plus 2. So let me write that down here. So x plus 1 over 4 times 1 over 2 times natural log of, I could put it in absolute value, but not necessary, because u squared is always positive and 2 is always positive. So we can just simply say parenthesis u squared plus 2 in here. Okay. If we were not sure that this is always positive, we could just easily put it in absolute value. That's all. And then this one would be minus 4, the same story here, right? So here we have minus 2. Well, I'm just going to use that scratch paper again so I can use space on my paper there. So taking the integral of that, we could write natural log of, or parenthesis, u squared plus 2. Then if we stop there and test it, and test this, we end up, what's the derivative of this? It's 1 over u squared plus 2 times, by the chain rule, times 2u, right? But we have a 1 there, not 2u. So we have to divide this by 1 over 2u, or let's see. Oh, so this is actually easier than that. So this is, so sorry, no, this is, let me correct myself. So this was u, this is has 1 as the numerator. Let me bring back this formula. We're going to apply that one again, this formula, because of the 1 we have. And we can write 2 as a square root of 2. So that'll be a lot easier. So applying that, it will be, so in this case, integral of u squared plus square root of 2 squared du, right? I just rewrote that as that. Now applying that formula, we would have 1 over square root of 2 times inverse tangent of u divided by square root of 2. Oops, sorry. I was off the screen there. So 1 over square root of 2 times inverse tangent of u over square root of 2 plus c. So we're just going to have that as the integral and of course multiply it by 1 over 4. So let's do that. So minus, that minus 1 over 4 times, I'm not going to, I did it here, so I'm not going to rewrite it, but that 2 can be written as a square root of 2 squared. That's the same thing as 2. And then so we have 1 over square root of 2, that's where that square root of 2 is coming from, times inverse tangent of u divided by square root of 2 plus c. Okay, like that. So we have here x, and this is in u, right? So we need to convert all of the u's to the x term as we had it here. We said u equals 2x minus 1. So knowing that u is equal to 2x minus 1, then I'm going to replace. And so what do we get? We get x plus 1 over 8 and 1 over 8. Well, I think I have enough room here, maybe. Maybe not. Well, let's see. X plus 1 over 8 natural log of u squared, so 2x minus 1 squared plus 2, right? I just substituted that with 2x minus 1, minus 1 over 4 square root of 2 times tangent, inverse tangent of that, 2x minus 1 divided by square root of 2 plus c. And so what do we have then? I guess I can fit the rest of it here. We can expand this and simplify it a little more. And I think it should fit right here. X plus 1 over 8 natural log of 4x squared minus 4x plus 3 minus 1 over 4 square root of 2 inverse tangent of all of that. So all I did was expand this and plus 2 and simplify it. That's all. From that step to here. And then 2x minus 1 divided by square root of 2 plus c. Oops, like that. Like that. Okay. Okay, so then next let's see, we have, I guess I can then, so that was page 12, so this will be page 13 then. Page 13. Maybe I can use one of my Sharpies to make this correction. So this is page 13. Page 13. And then, so this is case 4, right? Case 4 being if we have a rational expression such that the QX or the denominator contains repeated. Remember the previous case 3 was non-repeating irreducible denominator factoring, right? Factors. But here this is repeated irreducible or non-factorable quadratic expressions in this form. R being something greater than 1, 2, 3, and so on. So then the partial fractions will be of this form. So A1 x plus B1 and so on. Okay. So let's just do one example here. So that's of this kind, and I will change this 15, page 15 to 14. That's 14. Okay. All right. So just because you've seen enough examples right now that you can just go at this and see how far you get and if you're able to solve this all the way. Okay, so please pause the video, do this on your own, spend no more than 20 minutes on it, and then come back. All right, so I'm assuming you've done that. So we have, we need to break this up into its factors. So I will start by x to the 4th plus 1 divided by x times x squared plus 1 squared equals, x is linear, right? So I'm just going to say a over x plus, then this is a repeated quadratic factor. So I'm going to say bx plus c over x squared plus 1, and then plus dx plus e divided by x squared plus 1 squared. Okay. Multiply both sides by this denominator. What do we get on the left? We get just x to the 4th plus 1 equals. On the right, we have x and x cancel. When you multiply this first fraction by all of this, x and x cancel, you end up with a times whatever is left, right? X squared plus 1 squared. When you multiply this fraction by all of this, x squared plus 1 cancels out with that. We end up with bx plus c times x times another x squared plus 1 that is left over from our multiplication. Okay, and when you multiply this fraction by all of this, the denominator, x squared plus 1 squared and x squared plus 1 squared cancel out, we end up with just x which multiplies by that. So dx plus e times x. Okay, now we want to simplify. Before we simplify, if you look at this, I mean, this was something that I noticed in the solution book for this, and they kind of are creative, get creative at this point. They notice that everything here is, these two terms are multiplied by x, right? Because after all, what are we looking for here? We're looking for value of a, b, c, and d. So they notice that if you substitute for x with 0 at this point and here, and also here on the left, we're going to get a equals 1, which is a nice trick. And it's quite creative because right off the bat, at this point, you can solve for one of the variables, a. Right? So let's do that. Let's make use of that. So I would have never thought of it, but I noticed it in the solution book, which is a good technique. So to find a simple solution, this is what they had done. I would have, as you noticed in the previous examples, how we set up the systems and go from there. So I would have looked for value of a at that point, but not this early. But this is quite creative. Sometimes things work out this way, which is nice. So to find a simple solution to one of the variables, let x equals 0, and these two terms drop out, right? Therefore, we can solve for that. That drops out, we get 1 equals a. So therefore, a equals 1. That's quite creative. And this was suggested by the authors of the textbook. So I thought it's nice to mention it here as well. Okay, so now we have just B, C, and D to worry about, right? But let's actually now go ahead and set up our system. But before that, we have simplification to do, right? So x to the 4th plus 1 equals a times x to the 4th plus, so if you expand this, we get x to the 4th plus 2x squared plus 1, and then plus, in here we get bx squared, right? I'm just distributing the x into that. Bx squared, and then x, or plus cx, times x squared plus 1, and then plus that, plus dx squared plus ex. And then let's distribute, so we get a times x to the 4th plus 2a x squared plus a, and then here we get b x to the 4th plus bx squared excuse me, plus cx cubed plus cx. It's that. Okay. So do we have x to the 4th? Yes, we do. Let me take a sip of water here. So we have this term and that term. So we can write a plus b times x to the 4th. Do we have x cubed? Yes, we do. We have just that one. Plus, do we have x squared? Yes, we do here, and then here, and then here. Let's factor those terms out. We get 2a plus b plus d times x squared plus c plus e plus a. Okay, so we already figured out a equals 1. That's nice. So then, looking at this, a plus b should be equal to 1, right? So let me write that down. Then c should be equal to 0 because there is no x cubed term on the left. So c already, we also know, should be equal to 0. Then 2a plus b plus d also should be equal to 0 because we don't have an x squared term on this side, right? So 2a plus b plus d should also be equal to 0. We already know in this equation a equals 1, and so we end up with, here from the top system, from these two, so since a is equal to 1, b has to be equal to 0 if 1 plus b is to be equal to 1. So b has to be equal to 0, right? So let me also write that. B equals 0. So we have that figured out, this one, and c equals 0. If we substitute for b and a here, d, we can solve for d very easily, right? That would be 2 plus 0. D would be equal to minus 2. So d equals minus 2. And then lastly, c plus e. There is no x term on this side, right? So c plus e should be equal to 0. C is already 0. 0 plus e should be 0, so e is also equal to 0. Like that. So we have all of them figured out pretty quickly. So now we're going to go back with these values, including that, A, B, C, D, E, 5 values, and replace in here, A, B, C, D, and E. Okay? So thus, with that in mind, we have A over X. I'm just going to write them down again here so it's on the screen. So substituting for A with 1, we get 1 over X plus B is 0. C is 0. 0 divided by that is 0. So this whole term drops out, right? We end up with D being minus 2. So minus 2x plus E, which is 0. So minus 2. So we get minus 2 times x minus 2x divided by x squared plus 1 squared. Okay? So now we can easily integrate what we have here. So let's set it up. So we started with, originally we started with this expression, x to the 4th plus 1 divided by x times x squared plus 1 squared dx equals, and so we end up with that, right? So that 1 over x minus 2x over x squared plus 1 squared dx. So the first one is quite easy. That's just natural log of x, absolute value of x. The other one, let me notice that if it was the format that we have an x, we have 2x in the numerator, we have x squared in the denominator. So if we write down to integrate that, if we say, okay, integral of, move this up a little bit, and again, I'm doing this scratch paper thing because I have just a little bit of space left. So let me do this on the scratch paper. So we have this minus 2x over x squared plus 1 squared dx, right? Because the derivative of this x squared is 2x. it'll work nicely if I say, oh, the integral is natural log of, or not natural log, but let me, so 2x x squared plus 1 to minus 2 power dx, right? So if I take the, if I integrate that, what do we get? Just this piece. Just noticing that the derivative of this x squared is 2x. That's helpful because look what happens when we integrate just this piece. We'll get x squared plus 1 to negative 1 power divided by negative 1, right? If we integrate it. But if we leave it like this, what happens is, let's test this. So we have this minus, right? Let's keep it here. So we have minus x squared plus 1 to minus 1, right? So let us take the derivative of this now, just to test if we get this back. So we get minus, so we get minus x squared plus 1 minus 2 by the chain rule times 2x, right? We get 2x, but 2x is already there, so that's what we want. So really the derivative or the integral of that, the integral of this works nicely if we just say plus, because the minus will make this positive. Let me bring this back. When you integrate that piece, you get this. This minus will multiply whatever coefficient that is here, make it the opposite. If it's positive, makes it negative. If it's negative, makes it positive, right? In this case, we have a negative here, so it makes it positive. This minus times that minus will give us positive, and then 1 over x squared plus 1. And this being x squared plus 1 to negative 1 power. When we put it in the denominator, it will end up with positive power. And of course, because this is an indefinite integral, I have to remember to put a plus c. Okay, so that'll be that. So now if you take the derivative of this, you should end up with this piece, minus 2x over that. Let me grab another piece of paper here, scratch paper. Let's take the derivative of this to make sure that we end up with that. So that is actually x squared minus 1 to minus 1 power. Take the derivative of this with respect to x, or d dx, equals minus 1 times x squared plus 1 to minus 2 power times 2x by the chain rule, right? So we end up with minus 2x divided by x squared plus 1 squared. This rewritten in positive. And that's exactly what we have, right? Compare this with that. Okay, so that's that. So that's the integral of that expression. So this is one application of partial fractions. You'll see a lot more partial fractions when you reach calculus 3, and also differential equations. You'll see them again. So it's a very useful technique. So please keep it in mind. Don't forget about it if you're taking those other classes later on. So I thank you for persisting through this video lesson. I hope it was useful, and I'll see you again next time.